When we know an equation represents a function, we like to write that equation in a special notation called function notation. In function notation, we sub out the output variable, say y, and we write in place of it the name of the function. In this case, often we call it f, and then in parentheses the input variable. And we say out loud f of x. So it's the function f where it has the input of x. So we say of x. This is just a special way of notating a function. The variable x is actually called the input variable with functions because you input it into the equation and you calculate y, so y is called the output variable. In sciences, you'll often hear x also referenced as the independent variable because it comes first in the relationship because you put it into the function, and then y is the dependent variable because it depends on what you plug in for x. So you'll see input and independent kind of interchanged in math and science, and output and dependent also as words that are interchanged when related to an output variable. So here's an equation we know is a function from an earlier example, y equals negative 3/4 x plus 3. Because we know this is a function, we can actually write it in function notation. Now let's give it the name f. So instead of writing a y, I would write f, and then in parentheses the input variable, which I can see is the x here. So f of x equals negative 3/4 x plus 3. Now, one of the advantages of writing in this notation is that if I had, say, 5 functions that I was working with, I could give each one of them a different name, and it would be very easy for me to discuss them with people. Instead of saying the entire equation, I could say, well, the function f, or the function g, or the function h. I would just have to use the name of the function. Another thing that makes it very useful when working with function notations is that I can actually find functional values, or we'll learn y values, and notate them very easily, connecting them with their x value. For instance, now that I have this written as f of x, I could find f of 8 and f of negative 2. Now, what are f of 8 and f of negative 2? Well, f of 8, if we look at it, what this is I've taken the 8 and I've put it in the place of x. What I'm saying here is that x is now the value of 8. So I can make x 8 in the rest of the equation of the function. So I'm basically plugging 8 into that function. I'm going to erase this so it looks a little nicer. Then we calculate. So calculating this, I would have negative 3/4 times 8 over 1 plus 3. 4 goes into itself once and into 8 twice. So this is negative 6 because negative 3 times 2 plus 3, which is negative 3. So what I end up with here is that f of 8 is equal to negative 3. This is called evaluating the function. When I evaluate the function, I'm plugging a number in for x and actually figuring out the corresponding output of y, which is negative 3. So this is, in this statement right here, I am showing you an x value and a corresponding y value. So if you plug in 8, you will get out negative 3 for y. Another way to think about this is that this is actually just a point. F of 8 equals negative 3 means you have a point at 8, negative 3, because another way we can correspond an x and a y value in a relationship is writing it as an ordered pair. So it means we have this point at 8, negative 3. Now, keep in mind that these are two different statements. If you're working with the graph, you would talk about the points. If you're not working with the graph, you would stick to this notation that I'm circling here. F of 8 equals negative 3. You generally don't bring up the points or write it in point notation or ordered pair notation unless you're working with the graph. Now I had one more here, f of negative 2. What this is going to give us is the output or the y value when x is negative 2. So put a negative 2 in for the x and calculate. So when I calculate, notice I'm using a chain of equalities. I have a negative 2 over 1. I can take a 2 into itself and into 4 would be twice. So negative 3 times 1 is, actually it's a negative 1, is positive 3 over 2. I should probably go back to my original color. So that's 3 halves plus 3. To add a fraction and a whole number, I need to get a common denominator. So 3 halves plus 6 over 2 would give me 9 halves. So f of negative 2 is equal to 9 halves. So when x is negative 2, I get a y value on output of 9 halves. Let's practice working with function notation. Here I have 3 functions labeled. Function g is equal to x squared minus 2x minus 5. I have function h defined as h of x equals the square root of 6 minus 2x. And I have function k defined as negative 2x plus 7. Now, in the questions below, I'm going to ask about one of those functions. You want to use the name to know which one you're working with. So in part A, I say evaluate h of negative 15. Because I say h here, I'm only going to work with the function h. So h of negative 15 means I'm taking that negative 15 and plugging it in where I see the x in that equation. So I have square root of 6 minus 2 times negative 15, and calculate that with a chain of equalities. That would be 6 on the inside. Negative 2 times the negative 15 would be positive 30. That would be the square root of 36 on the inside, and the square root of 36 is 6. Notice there was no plus and minus on the outside. It wouldn't be a function if there was a plus and minus. The square root by itself always returns the positive. So what we have here, if we kept going, this would be h of negative 15 equals 6. You don't have to have this little dashed line or this little crooked arrow here. I was just kind of pointing out that what we started with was h of negative 15, and we found that that was equal to 6. Let's do that again. Evaluate g of 3. So now we're working with the function g. So we're over here now. The function g says take the x value and square it. Often it's a good idea to put the value in parentheses. Minus 2 times that x value, which is 3 minus 5. Calculate. Always square and multiply before you add and subtract. So we get 3 squared is 9, 2 times 3 is 6, and then the minus 5. 9 minus 6 is 3. 3 minus 5 is negative 2. So we end up with g of 3 equal to negative 2. In part C, the question is phrased a little differently. Here we had evaluate the function for an input value. Now notice it says solve g of x equals 3. Solve is the first hint that we're going to be doing something differently. The second hint is that in the other problems, I gave you a number inside the parentheses, so I was giving you an x value. Here I'm saying we don't know what x is because x is showing up by itself, but we do know that that whole thing is equal to 3. Well, what this is saying is the whole function is equal to 3. So if I take the whole function g, which is x squared minus 2x minus 5, that whole thing equals 3. And when we see it in that format, the word solve makes sense. I want to solve this equation. That's all that is saying. So I'm going to solve this function equation. X squared minus 2x minus 5 equals 3. This is a quadratic equation because of the x squared, so let's get 0 on one side. Let's move that 3 over. Negative 5 minus 3 is negative 8. Then factor the other side. So we get x and x. Negative 8 factors to negative 4 and positive 2 to result in a negative 2 in the middle. So x minus 4 equals 0. It gives us x equals 4. And x plus 2 equals 0 gives us x equals negative 2. So we actually get two solutions. So the solutions here are 4 and negative 2. So here are 3 more very similar problems. Maybe pause the video and try those on your own, and then you can see me work through the results. Okay, so if you've unpaused, let's go through these real quick. G of negative 6, we're using the function g again, so I'm going to take -6 and square it, minus 2 times -6 minus 5. Calculating, I get 36 plus 12 minus 5. 36 plus 12 is 48, minus 5 is 43. So g of -6 is equal to 43. Again, you're putting an x value of -6 in and figuring out the y value is 43, the corresponding y value. If you wanted to, you could write that as an ordered pair, but we're not working with a graph here, so generally you wouldn't. K of 5, we're now working with the function k. Put a 5 in where you see x, -2 times 5 plus 7. Calculate, -10 plus 7, that's equal to -3. So k of 5 is equal to -3. So in our last two examples, we were evaluating the function for a particular x value. Our result gives us a y value. In this last example, this is saying k of x equals 8. That's saying the entire function k of x is -2x plus 7, is equal to 8. That's why we say solve. We end up with an equation, we write that out. So now to solve this, we would subtract the 7 from both sides to get 1, and then divide by -2, so we get -1/2. So the solution is -1/2. One last comment. When we solve equations in Part C and Part F, we could very easily check our answers. To check the answer here, in like the last one I did, Part F, we could go up and go to the original k function and plug in as an input -1/2 and see if we got that 8 out. So -2 times -1/2. If we were to multiply that and then add the 7, would I get the 8? Well, -2 times -1/2 is 1. 1 plus 7 is 8, and that does check. You could do the same thing up here in Part C for the values of 4 and the values of -2. Just try plugging g of 4 in to this equation here, and it should come out to 3. So I'll let you try that, and then g of -2 should also come out to 3 if you have the right results.